Okay, so in this lecture, we're going to do the second case for the wing spar, which basically is the same problem as before, but this time the web will only be effective in resisting shear and no bending. So let's say for the same problem as in lecture 8, okay, but assume web slash panel only effective in shear. Okay, so in this case we are dealing with case 1. Okay, so let me just do a very quick figure again. So it's not too good, but let's say this was clamp. We're looking at the cut, which was right in the middle. That distance over here is 200 millimeters. This one over here is 400. And then this cut here was at 1000, and the overall length is 2002 meters. Okay, now the areas of this, we had to do a boom. B1, B2, this was equal to 400 millimeters square, and the thickness here of the panel was equal to 2 millimeters. Okay, all right, so basically what happens at the cut? So at the cut, oh, I forgot to draw the force, and here we had a force of F equal 20 kilonewtons. Okay, so what would be the moment at the cut? So the moment at the cut will be an X, because of a reference frame, will be equal to what? Will be equal to the 20 kilonewtons, will be force times distance. So will be 20 kilonewtons times that distance, that will be 1000 millimeters. So this is going to give us that X will be equal to 20 10 to the 6 newtons per millimeter. All right. So by doing this, we know that the load so we have the that's 1, that's 2, so the load the flanges is what? So remember, we're going to have two components. Okay. One would be the, we can do a little sketch for the top one. P1 will have one components. Okay, the P01 and the P11. Okay. So if we go to the notes, we know that Pz1 will just be equal to the moment divided by the depth of this one, which at this location, this is 400, this is 200, the middle would be 300. So this will give us what? 20, 10 to the 6 divided by 300, and then the one at the bottom will be Pz2 equal mx over h equal to 20, 10 to the 6 divided by 300. So this gives 66,666.67. Okay, newtons. And now we need to be careful. If this is the force is coming this way, that means that the top will be in tension and the bottom will be in compression. So this will be positive tension, this will be negative. So this is tension, and this one will be compression. All right. So now we need to find the vertical component of the load. Okay, so the vertical components . Py1 and Py2 will be equal to what? So we'll have Py1 will be equal to Pz1 by definition tangent alpha 1, which we know it will be equal to Pz1 delta y1 over delta z. Okay, and Py2 will be equal to Pz2 tangent alpha 2, which will be Pz2 delta y2 over delta z. Okay, you can look at the previous lecture, but basically what would be the delta y? Delta y is the change in height. So between this point that will be, let's say, 400 to this one will be 300, will be 100. Or you want to look at it, this will be 200. So it will be 400 minus 300. Okay, so yeah. So the overall change in length, sorry, will be 400 minus 200 will be 200. Sorry, will be 200, half of it. Oh, okay, no, I'm getting confused because I'm going, you can either do from here to here or from here to here. So if you go from, let me go back to the notes, would be easier. This I think is open here. Yeah, so this is the example. So that's the difference. We did all these calculations, and then to find, let's say here, okay, you can either go from here to here, that will be 200 minus 100 is change in height of 100, and you go from this point to this point, so it's divided by 1000. or you can go from the changing height, let's say from here to here, or from here to here would be 200 minus 150, 50, or 150 minus 150 divided by then just that distance, or just that distance, which is 1000. And since it is symmetric, this one is the same, so it's 1 over 20. Okay, that way I don't have to repeat it over here. So this one over here, we know this is 1 over 20, 1 over 20 from lecture 8. All right. So now we can just go and simplify, and we're gonna get that P11 equal to the 66,666.67 times the 1 over 20, and this gives 3,333.33 newtons. And similarly, we're going to get that Py2 is equal to 6666.67 times 120 equal to 333.33 newtons. Okay, so as before, remember that with that figure, this one is going down, and this one, the y, be going up. Okay, so basically this is what we have. P12, PC2. Okay, so this one goes down, this one goes up. It's the same figure as in the previous lecture. So and now if I do the figure here to find the shear force, so the shear force in the panel / web will be what? So do this. All right. So we say that Py1 is going down because the web is going down, like this figure over here, and now this one will be going up. Py2, now this one you can do whatever you want, up or down. This will be the V on the web, and let's say this should be equal to the total shear force or the force outside. So let's say if I plot it this way, okay, let's say this will be V, but this is external, okay? So external force, which really should be equal to what? To the F force, which is equal to 20 kilonewtons going down. So really here what we're doing, I told you these two methods. You can either do summation of force equal to 0, but personally I like to do more like summation external will be equal to the internal. I think it's more representative. So what happened? This is the external force, okay? So this will give us what? V need to be resisted now by the structure. Okay, so on the structure, what do we have? Vy web minus Py1 plus Py2. Okay? And now over here, we needed to be careful here because what do we say? Yeah, maybe here I put it wrong. Here is P2. The bottom, the top is in tension, the bottom is in compression, so this is negative over here. All right. Which should give us a negative value over here. and it should be a negative value here. So now what happened? So from here we can find that V shear force on the web will be equal to what? V plus Py1 minus Py2. I mean, if you think about this, this makes sense, okay? The web is going to have to carry whatever load this is carrying minus whatever the two flanges are carrying, all right? So logically, we should get what? The 20,000, the load 20,000 minus whatever each one of the flanges is carrying, okay? So it would be 20,000 minus the Py minus will be what? Minus twice the 3,333.33. So let's see what the math is going to give us. So 59. Okay. Where we say that V will be equal to minus 20,000 newtons. Okay, this is the 20,000 kilonewtons. Then we get that Py1 was equal to tension, so it's 3.3 newtons. Py2 was in compression, so it's the same thing but negative. Okay, so when you go and substitute into the equation, you know, get that Vy will be equal to what? Minus 20,000 plus 3,333.3 minus 3,333.3 okay. So this will give us what? Vy web equal to minus 13,333.34 newtons. Okay, so basically this is the total load, external load, minus what? Minus what each one of the flanges will carry on the y direction. Okay? So now for case 1, we know the shear flow in the web is constant. So for case 1, okay, we know that the shear flow in the panel slash web is constant through the depth of the spar or wing. Okay, so we know QS over here will be equal to what? Vy web over H. Okay, so positive, negative, doesn't matter, depending on the sign convention you take for the shear, but it's not that important. Okay, let me go back for a second here to lecture 8. Let's see, we have something. For case 1, this is a problem. Okay, so this is the constant throughout the shear. All right. So then the local application will give us so that QS will be equal to 13,333.34 divided by the depth of the cut, which is 300, and this is going to give, we're going to put the minus 44.45 newtons per millimeters. Okay, so we know over here is constant, so that means that this is, if this is B1 and this one is B2 at the section AA, we know that the thickness here was 2 millimeters, so this one should be constant over here. Really the value, the sign doesn't matter, what's important is the value. And this value here would be 44.45. Newtons per millimeter. Okay, so what's important over here to notice is what? Is that, let me maybe go to the next page. All right, 60. So let's say here summary. Okay, so what is the summary? For the example we just did, which is case 1, what did we find? We found that Q is constant and equal to 44.45. Just want to look at the magnitude, okay? So if you do the distribution, B1, B2, we have this over here, okay? 44.45, and the distance here is 300 the depth, okay? This is really H. In case 2, which now we said the web is also effective in bending, we had a complicated expression, so Q was in function of S. So let's see if I can go back to that page. All right, so let's wait. So this is the equation. So we had, you see, QS now for case 2 will be in function of S. And in the problem we did, we found that that expression for QS was equal to this expression here. And that gives you a distribution, you see that it's not constant. All right, so the distribution is $39.14, and the max value is 53.8. All right, I just redid the figure here. Okay, so what is the importance over here to see is that if you do the analysis using case 1, you get a maximum value of 44.45. But, and if you do it with case 2, you get a maximum value of 53.8. So what happens is that this one will give you some type of average value. So if you do a calculation of the area of 44.45 times 300, it's probably pretty close to the area as if you do 34.14 times 300 plus the area of the semicircle, okay? So this one will give you a correct value on the average sense of what is happening in the structure, but this one will give you a more realized distribution of the load, giving you the highest value. So the percentage difference between case 1 and case 2 is approximately 17%. So you see that whatever you do on the assumption in solving your problem, you can end up with a considerable difference in value. Okay. All right. So on the same video now, I'm going to use the same file that we had before in Nastran, but now I'm going to do it for case 1. Okay, very quick. Alright, so this is what we have: 59, 57, 58, 59, and 60. Okay, so let me get organized. And now, okay, so let us do the final element for case 1. Do you remember before we did save the geometry? So I'm going to reuse it. And same process. First thing to do is to create the material. Really, you could put any value here, but I like to use a real material that will be the aluminum 2024 T6. Okay. Cancel. Now we need to define 2 different properties. So let's look at the shear panel. Okay, one, don't forget to do this over here, otherwise it will give you some error. And then here, be careful. I know the problem said that the thickness is 2, but okay, thickness is 2 on the Z direction, okay? And here we're looking at the shear on the Y direction. So be careful, just put 1 over here. Basically, if you put 2, you will need to put 2 in this direction, not on the depth direction. If you put it 2, you're going to end up with the value of the of the shear throughout the cross section of the plate, not throughout the cross section of the wing spar. So basically, if you are here, you will be calculating in this direction here. Okay. So F8 XY. All right, so the other property we need to create is the one of the rod. Oops. So what did I do here? Let me see what happened with this property. No, that's correct. So property new, rod, and we know this one was 400. Okay, cancel. Mesh control, size on surface. We set to use 100. Okay. Cancel mesh geometry surface. Okay. Shear property. All right. Mesh geometry curves. 1, 2, 3, 4. Okay, with the rod property. There we go. Tools. Check coincident nodes. Select all. Okay. And all the nodes on the boundary should be okay. Redundant. So done. Review. Okay. All right. So model. Constraint, let's say on curve, clamp, okay, fix, okay. I don't think we change the result, but if you want, we can put the load in just one node over here. Before doing that, maybe go here to F6, node ID, apply, okay. And let's see what is the maximum number of nodes. Looks like it's 105. So if we create one extra node, it should be 106. Let's see what would happen. Custom machine spider method on curve. So that one. You see it created here 106, which is on top of 23, I think. Okay, so model load not all. So this is the force, which is equal to 20 kilonewtons. Okay, node 106. So we have it here. Let's just leave it as it is. More, okay. Minus 20, 1, 2, 3, because it's kilonewtons. Okay. Basically, what this is doing is that instead of applying just the load at this node, it will be pulling from all these nodes at the same time. Okay. So F8, XY, okay. So I think that's it now. Let's see. Okay. Okay. So is it already an analysis here? No. Analyze, manage, new. Okay. Analyze. All right. So again, we need to look at the section at 1000. So tools, work plane. So we can see where the 1 meter is. Group new. Section A. What did I do here? Section AA at 1000 millimeters. Group elements ID, and we just want the shear. I mean, we could look also at the actual load if you want. We can do that later. Okay. All right. So now F5. Got contour first, deform, shear panel average. Okay, okay. All right, maybe to do F6. No labels. Apply, okay. So you see distribution, instead of just having a red over here, is more uniform. And let's do F5. Criteria, okay. So let's go here on groups, active group, show active group, and we have this one. You see that is constant between 43 and 46, and let me go back to the notes. And before we had for that one. All right, so let's see, can do this. We had a value, you see, of 44.45, which basically is about the average of these two, okay? And you see the value will be constant throughout the cross section. All right, something we did not calculate, but if you want, we could do it, okay? So let's say now show for group, and let's try to create another group. Let's see what would be the actual load on these flanges, okay? So let's see what can we do with this. Group, new, let's call it top flange, that we know should be in tension. Okay, so it should go here from a value to all the way here to 0. top flange, group, elements on curve. Alright, let me do one thing here. I don't know if it will help or not, but we don't want to take the shear, so group, elements on curve. So hopefully if they are not active, they're not going to be considered. So show active group, it should show nothing, okay? Because these properties mean this contour is for the shear panel property, and for the rods is this one. So rod axial stress, rod axial force will be the same thing. Okay, and here probably the best thing is to do a beam diagram. Okay, so you see it goes from a value over here, which is about 98,000, so probably it's a bit high, it's probably 100,000, to basically here to 0, okay? And this will be like we did before in order to calculate it. So this one is in tension, and I will do the lower one, it should be the same values but negative in compression. Alright, so I think this will finish this short video, okay? But again, let's go back to this one. Show active group. That one should show nothing, so F5 again here. Criteria, form, I think it was 6020, yeah. There we go. Let's eliminate the work plane. So you see over here it's constant. Okay. And if we over the previous model that we had, let me save this one first. File, save as model 1. And if we open the one we had for case 2, I think it's this one. You see here these values are not constant. So it went from I think 39 point something to 50 point something. So it was constant over here, then like a half a circle, so a quarter of a circle, half a circle, and then constant again. So you see it's constant, 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 but this one is more like this way. All right. So that would be the end of the video.